Today we're going to start chapter number 4, and the title here reads The Origin of Modern Astronomy, and we always start with a guide post. The previous chapters gave you a modern view of what you see in the sky, and now you're ready to understand one of the most sweeping revolutions in human thought, the realization that we live on a planet. In this chapter, you will discover how astronomers of the Renaissance overthrew an ancient theory and found a new way to understand the Earth. Here, you will find answers to 4 essential questions. How did the ancients describe the place of the Earth? What is the real contribution of Islamic astronomy? How did Copernicus change the place of the Earth? Why did Galileo condemned by the Inquisition? How did Copernican astronomers solve the puzzle of planetary motion? This astronomical story will introduce you to the origin of modern astronomy and will help you answer an important question about science. How do we know? How do scientific revolutions occur? The outline, the first one will talk about the roots of astronomy. Then briefly we'll deal with the era of Islamic astronomy. Then we'll talk about Copernican revolution and the puzzle of planetary motion. So we'll start with the first part, which is the roots of astronomy. If you remember in the first lecture, I told you now we live in a universe, and the estimated age of the universe is 13.8 billion years. And when it comes to our solar system, which is the Earth that we live in, it's about 4.6 billion years. Now, maybe in chapter number 6, we'll talk about this. But when we come to our history as humans, the estimates now, when we talk about the history of humans on the Earth, I think it's about 200,000 years. And that's basically the evolution. Okay. Now, when we come to humans basically start forming societies and develop agriculture and so on, so we need to go back and look at that. So when you look at any archaeological digs, or we talk about history books, we always start from the Stone Age, where humans were making tools from stones. And then we went to the Bronze Age, when humans basically start making metal tools and so on. But this is all has to go to archaeological digs, where you want to find out how did the communities were forming and civilizations and so on. But when we want to look at evidence, we want to look at recorded history for anything that we want to do. So when we try to look at the roots of astronomy, I am sure, or many humans basically, they relied on things that they saw in the sky, but when actually they start making records of these. And if you look at any civilizations, it was essential that they needed water sources and fertile land where they can plant things. So you find one of the early civilizations were basically formed on the banks of rivers, either if it's in China or India or the Babylonians and the Euphrates or the Egyptians on the Nile. So it's always, they needed these elements. And when humans, they start settling down and they start farming, so now they have more time to pay attention to other things and find things that can help them, especially when with agriculture, they have to know seasons and so on. And astronomy now plays a role. So if we look at the Babylonians, or the remains of the Babylonians, and we see how they developed the counting based on 60s and so on, and how they were looking at the sun in the sky. And the Egyptians, where they lived on the Nile and they were faced with floodings, and they wanted to know how they can know when this is going to happen. So they looked at the moon, and from the moon they can tell that the month is about 30 days, and the cycle when this flooding is going to repeat and so on, it's about 12. And astronomy became very important, and it's adopted in their monuments. So usually we look at these old ruins and we try to see if there is any astronomical significance in their buildings. And sometimes what you see is inscriptions on walls or things like that, but we really need documentation. And the documentation came with the Greeks. Well, that doesn't mean they are the ones who originated astronomy, but they actually start in the documentation. And sometimes they said that the Greeks learned from the Egyptians, and there are evidence of these things, but some also argue that yes, they interacted and they learned from the Egyptians. But when you look at the statues of the pharaohs, you find them rigid, but the Greeks have their statues are more dynamic and so on. So they created their own civilization or improved on it based on what they learned, but they're credited with the documentation. So they start documenting things, and we'll talk about this a little bit later. So this is what we usually, if you look at the slide that I have here, and when we try to look at the roots of astronomy, and the first, it says, as unfortunately, there are no written documents about the significance of a stone on Bronze Age monuments. And then the second here, it says, first preserved written documents about ancient astronomy are from ancient Greek philosophy. This is documentation. So documentation is very important. And now the Greeks basically start documenting things, and they left documents. By the way, most of these documents, they could have been lost if it's not for the Muslims who started their civilization with what we call Asr al-Tarjuma, or the era of translation. So they actually looked at everything that was available. They translated that, and of course they start looking at it in a critical way to see through it, to see what is right and what's wrong and so on. So really, we cannot really tell when humans were start developing astronomical model and things like that, because we cannot tell about, we do not have good documentation about the Stone Age and the Bronze Age, but we look at the monuments and we can tell. Of course, these are countless. I think one of them, and still many marvel, are the pyramids in Egypt, and the pyramids still standing. But at the time, I think they were in the desert, and the sun strikes them, because what you see now as big blocks of stone, it was covered with granite, and when the sun hits it, it gives a spectacular show. But now, of course, all of that is taken or stolen, whatever it is. Now, in the UK, there is a monument which known as the Stonehenge, and it's big blocks of stone arranged in this way. And there is a stone here, which you can see, and this is what we call the hail stone. And many argue that this was basically for paganic worship and so on. But those who looked at it carefully, they said, well, basically the sun comes in the top of the hailstone in the first day of summer. And many basically start trying to see some alignment. So they said this actually had some astronomical significance, where it could be used as a calendar, or also to signify the beginning of seasons and so on. So that's one of the monuments. Okay, it's not as spectacular as the Egyptian pyramid, but maybe it's older. In the United States, in New Mexico, there is a crack in between rocks that makes the shape of a dagger, and there's someone who basically made a spiral like this, where the dagger basically cuts through that during the first day of summer, and indicating that someone tried to signal, or they can look at the beginning of the summer, because it was important to them. And of course, if in South America, you can see the Maya civilization and so on, and these are all, I'm very sure that they have interest in astronomy, and it may have some significance. So there are countless number of old civilization where astronomy was significant to them because of seasons and agriculture and so on, and it may appear in their buildings. So usually when we try to go to the roots of astronomy, sometimes we call it archaeoastronomy, where we rely on archaeology and we look at these. So that I just gave a few examples here just to show you, but the credit for documentation goes for the ancient Greeks. And they used a lot of philosophy in trying to explain what they see in nature. Now, the Greeks, they actually started from what we call first principles. And to them, these first principles were believed to be obvious. بالعربي we can say المبادئ الأولية, and obvious means بديهي. So one of these first principle was a geocentric universe. Now, geo here, let me choose a different color. Geo here basically means Earth. And geocentric, that means the center of the universe is the Earth. So Earth here means geo, and when we say geocentric, the center of the universe is the Earth. And to them, probably this was obvious because we live here on Earth and we see things basically in the sky which are moving around the Earth, and actually they did not even know that the Earth is a planet. The second principle that they actually used is perfect heavens. And heavens here refer to celestial bodies. And they say what we see in the sky are perfect spheres. Unlike what we see here on the surface of the Earth, you have valleys, mountains, and things like that. So they said up there, it must be perfect. And the object that we see them, they're further away, that's why it's smaller. To them, that was also understood, but they thought of them as spheres. And these spheres basically go in circular orbits. And to convince themselves that probably the Earth is the center, they tried something that we call parallax. So you can, if you look at object, you actually see the object with your two eyes. So when you look at any object, you basically look at the angle that it's obtained to your eyes. So in the parallax, you can close one eye and open one eye, and with the open eye, you look at the object, but the object is far away. You can basically block that with your thumb. But now, if you close the eye that was open and you open the other one, the object moves to the other side and you can see it. And that was basically known as parallax. Now, the objects here are far away from us. So sometimes that's not easily observable, okay? And that's why they did not notice any parallax, and they became more convinced that the Earth is the center of the universe. So that's one of the reasoning. Now, parallax, just shortly, and sometimes we call that stellar parallax, and it can be used to measure how far objects are. So, for example, if you look at the position of the Earth relative to the Sun at 2 different times. So for example, you make an observation in February, and then you make another observation in August, and you look at an object in the sky, and you want to look at the angle that it makes, and you use a little bit of geometry, and we know how far is the Earth from the Sun and so on. We can basically decide how far is this object based on this parallax. But that's because of how the Earth is revolving around the Sun. So that's a technique is used in measuring distances to the stars and so on. And from time to time, this is fine-tuned, and you find the number changes and so on. So that's the way we use parallax now. Now the model of the Greeks, it starts with Hippocrates. بالعربي نحن نقول له Hippocrates. And he started with a model where the Earth is at the center and everything else is a perfect sphere, and it orbits the Earth in a perfect circle, or what we call uniform circular motion. Even the Sun itself. So this was the way the Greeks started looking at a physical model to explain what they see in the sky. Ptolemy, or depends on how you want to pronounce it, Ptolemy's بالعربي, he looked at this because there are some problem with the observations, to explain the observation, and he added something that called epicycles. And these were to explain what we see in the night sky. Remember in the last lecture, I told you about if you look at Mars from here, and during the course of the year, you can see that Mars does something which we call retrograde, which is a westward motion in the sky. And this was kind of a puzzle, but I told you in the last lecture, we see this because the Earth is closer to the Sun, and it revolves around the Sun at a faster rate than Mars. So sometimes Mars is ahead of us, then we catch up to Mars, and then Mars seems to fall behind, and that's what we see, this retrograde for Mars. But this was kind of a puzzle. So Ptolemy, to explain this, he said, well, yes, the Earth is at the center, and the major way or the major orbit of the Earth around of the planet or the star around the Earth, we call that the different. But to explain why we see this effect, he said, well, the object or the spherical object, they are not actually moving on the different, but they are having what we call epicycles. That means they go around this way, where the center of these circles is the circumference of this different. And this way, then you may actually see the object like Mars, for example, at different location, and that can give you this retrograde motion that is seen. So the epicycles were added in to explain this effect. So they actually made the Earth at one location. Then there is something that we call the equinat, and they added these epicycles to explain the model. And that was a standard model accepted. Aristotle later on adopted this model, and Aristotle was basically a revered personality in Greek civilization, and he added more spheres, and when he endorsed that, that became basically a standard model for or the physical model for celestial bodies. Later on, the Muslim astronomers in astronomy was important to them, so they translated the works of the Greeks, math and all of these, and they kind of adopted the same way that the Earth is the center, and no one can blame the Greeks or the Muslims for that, because it's something that we live here on Earth and we think we're special, and it must be that everything revolves around the Earth. That, of course, later on, after the fall of the Andalus, and then the rise of the Renaissance, that start changing. Even the church, they adopted the model of the Greeks in taking the Earth as the center. And of course, anyone that claims otherwise, you will be committing a blasphemy. And we'll talk about Galileo Galilei later. So a quick summary of the points that we just went through. Many cultures around the world observe the sky and mark important alignments. And that's what I told you, would we look at archaeoastronomy, but having no written language left no detailed records of their astronomical beliefs. Greek astronomy, which I told you, it's derived from Babylonian and Egyptians, is better known because written documents have survived. And we talked about the two principles that the Greek astronomers adopted in their physical model of how the perfect spheres are going around the Earth. And they believed in geocentric universe and perfect heavens. And the Ptolemy universe adopted the epicycle to explain the retrograde motion. So that was the accepted view through the written human history, that the Earth is the center of the universe. Now, this part here, when Muslims started their civilization, astronomy was an essential part. It was an important part because Muslims start moving from Mecca to different locations, and Muslims pray every 5 times a day, so they have to locate the direction of Al-Qibla wherever you are. Where is Mecca located relative to you? Now there is Ramadan, there is Hajj, so they have to know the beginning of every Islamic month, which is connected to the observation of crescent. Okay, and also the 5 daily prayers, where the location of the sun and so on. So astronomy was important to Muslims. Besides the importance of it for agriculture and so on, where you want to know the season and what type of produce you want to plant and so on. So that was important to them. And the Muslims start translating the works of the Greeks, and they start working on these models. But the Muslim introduced a new concept, and the concept that they introduced was the observatory. So now they start organizing science and making special places where you actually go and do science. And during the history of Islamic civilization, there are many observatories. One in Samarkand, Marha, Baghdad, Cairo, Andalusia, or an Andalus. So these observatories, they were basically dedicated for observation and astronomy and understanding what we see in the sky. So Muslim now played a part in advancing astronomy by introducing the concept of observatories. Not only that, they start basically introducing tools now to do that. Now, there are many names in the Muslim civilization. Okay, I think the famous one that most of you maybe remember is Abbas ibn Firnas, and I think he was the first one who thought of flying. And he looked at birds and he made wings, and of course he went through that. So he was the first one to basically think about flights and flying. Probably another personality here that you can relate to, Al-Khwarizmi, which algorithms that we use today. Ibn Sina, and I think in the Europe now they call it Avicenna, and he's a great doctor. Okay. And he basically wrote a textbook in medicine and so on. So there are personalities through history that made significant contribution. I always, because I teach optics a lot, Ibn al-Haytham, and he's Al-Hasan Ibn al-Haytham. I think in Europe and Western civilization, they know him as Al-Hasan. They don't pronounce Al-Hasan. There is a big difference between Al-Hasan and Al-Hazan. These are big names. They were advancing science during their time. At that time, it was the medieval era in Europe. Okay. So these places or schools, okay, or observatories are accredited to these Muslim scientists. So now Muslim scientists start using this concept of an observatory, tools, textbooks to explain things to their credit, and they even came with the concept of universities. And if you look at the old traditional way that Muslim used to do things, usually you have a scholar and he has followers around him, and when any one of them basically get to the point where he can approve of his knowledge, they give them the turban, and they give them al-aba, which abaya, which looks like the regila. And this tradition, you can see it in many universities today. You can, when they graduate, they wear these things. Okay. So we humans, we copy from each other, and these things stay. By the way, if you look at the our calendar, we have 12 months in a year. We have 30 days in a month, more or less. And every day we divide that in 24 hours. I'm not going to go through that, but I am trying to make a point here. And then every hour is 60 minutes, and every minute is 60 seconds. But when we come to a millisecond, we say that a second contains 1,000 milliseconds. So we broke away. We kept, usually we try to use the hundreds and everything. But when it came to the hour or the minute, we stuck with the 60 that were developed or started with the Babylonians. But when it came to milliseconds and nanoseconds and so on, we reverted to using 1,000 and million and billion and so on, like what we do with other units. So sometimes we stick with things that we pick from different civilizations. Now, I'm not going to go through, these schools were important, and they actually were developing tools to make observation, and at the same time, they start seeing that observation and model kind of not agreeing, so they have to create tables, which called these, okay? And these were to correct for the observation that you actually see. Now in Baghdad, I think during the Abbasi Khilafah, or Khilafah al-Abbasiyya, Ibn al-Batani, I think, was a famous personality there. And he came to predict eclipses, and he was also gave some condition for the observation of crescents and so on. In Cairo, Ibn Yunus was one of the famous personalities there, and he made inventions and so on. In Maraha, it was Nasruddin Tusi, and I don't think he was fortunate, because his time is the time when the Mughals were invading the area. So I think he even worked with them. He wanted to do astronomy, and he kind of was working for Holako because the Mughals believed in what the sky says and so on. But I think he used it just to advance and further his observatory and his science. And sometimes scientists, they have to live with reality. Okay. And in Samarkand, okay, Baha is basically one of the famous personalities there. And if you use this place, visit this place, you will find some of the monuments and so on. So the idea of Muslim, they introduced the concept of schools, universities, hospitals, observatories. They start making places where it's specialized in delivering science or medical care or education. And of course, they came with tools to do that. And they wrote textbooks to explain these tools and so on. So one of the famous things in astronomy is the sun dial, where you can tell time. And I think there is one in Masjid al-Amawi in Damascus. And I have no idea what is the status of it now. Okay. There are many models that they were constructed to explain how these celestial bodies are orbiting the Earth. I think this is taken from a mall in Dubai. There is a mall called Ibn Battuta Mall, and it has different wings. And in the Persian wing, when you go in, you will see one of these things. Ibn Battuta was one of the explorers in Muslim civilization, so he was going around. Maybe that's they named the mall after him. But there are different. There is the Chinese, Egyptian, and so on. So when you go through that, you can see some of these astronomical tools that are there. This is the Maraha Observatory. Now they're trying to preserve it. Okay, it went through because it was damaged and so on. So they put a dome on top to preserve this. Actually, this is the Samarkand Observatory, and that's how it used to look. But what survived is basically, if you look at this door and what's behind this door, now this is what has survived. And if you go inside, you will see an arc like this, and the sun can enter, and you can basically tell where the sun falls and graduation and so on. So they use many tools and observatories where they can basically make observation. One of the famous tools is the Astrolab. It's, I think, a very complicated tool to use, but it was used in trying to predict locations and so on, the quadrant. And finally, you can see the concept here where scientists can gather, or astronomers can gather in one place, and they deliberate among themselves, and they use their tools to measure astronomy and so on. That's an artistic rendition to show you what was basically being carried out in these observatories. So the Muslims, during their civilization, they were basically credited with the introduction of observatory and tools to make these observations and so on. And many of these Muslim scientists, they actually grew worries about the Earth being the center. Some of them, they basically have some argument that this is not the right way. However, the credit goes to Copernicus, and that's why we call it Copernican revolution. And that was done in Europe. And Nicholas Copernicus, you can just pay attention to these dates. I don't want you to memorize them, but you can know them just to give you the events through history. He was born in 1473, and he died in 1543. So he lived for about 70 years. And I think he was a scholar, and he looked at many different works of the Muslims and the Greeks and so on. And finally, and many now argument maybe the ideas were not his own, but that's history now. He's accredited with a model in which he said that the sun is the center, not the Earth. And this is now the change from geocentric to heliocentric. And helio here meaning sun. So he presented a model, and in his model, the sun is the center, not the Earth. That was very courageous from him to say at that time, because the Catholic Church was dominant, and that basically goes against the teaching of the Bible to them from their point of view. So now Copernicus is credited with that. Now this is a stamp where in the US commemorating the 500th birthday of Copernicus. That was in 1973, and I think at that time the stamp is 8 cents. These prices are not around anymore. And these are different stamps from Poland and different places also honoring and commemorating Copernicus. Now in his model, the retrograde is explained nicely. Unlike the complicated way of the epicycles and so on. So it made Ptolemy's epicycle unnecessary now with this elegant model here. But he presented a model. And there are some problems with this model as well. And maybe it has to do with the observation. He assumed that the object orbits the sun in uniform circular motion. That means they go around in circles, and of course that will make them go with the same speed around the circle, and that's why we say uniform circular motion. But he's credited with this model in presenting the sun as the center and not the Earth. Now, we'll look at Galileo Galilei. He was born in 1594, and he died in 1642. So he was basically born after the death of Copernicus. So at his time, he was basically aware of that the Copernicus already presented a model where the sun should be the center and not the Earth. Now, Galileo Galilei was a good scientist, was respected, a good mathematician as well. In the end of 1608, by October or something like this, a Dutch lens maker, he made a patent on a telescope. So how can you make a telescope and things will appear magnified through the telescope? Galileo Galilei became aware of this fact. So he made a telescope of his own that can magnify things up to 20 times. And he pointed the telescope to the sky. So he is credited by now aiding the eye in making astronomical observations. Before him, nobody did that. They used tools, but they relied on the eyesight. But Galileo Galilei basically used the telescope. He did not invent the telescope. And that tells you about science. When scientists become aware of new things, they use them. So he started making observation, and when he looked at Jupiter, and Jupiter is fairly bright object in the night sky, is not as bright as Venus, and you can see here that's in 1610. So shortly after he started knowing about the telescope, and he made one and pointing that. So you can see here from January 7th till January 13th, And that's how, when he looked at Jupiter, Jupiter was not alone. So he saw object around Jupiter. And these basically were having different location when he made different observation at different nights. These now are known as, these are Jupiter satellites, which are moons, and these are known as the 4 Galilean moons. And then he looked at Saturn. This is basically, now, if you have a good telescope, that's what you see. But his crude telescope, basically, you can see these things. And we'll talk about telescopes in chapter number 5. Saturn, which to us looks like this, probably that's what he saw. And when he looked at the moon, and when you look at the surface of the moon, you see features like this. So that basically tells you that the moon has mountains and valleys and things like that. And to him, that goes against the idea of the Greeks, where the celestial bodies or the heavens are perfect spheres. And when he looked at the sun, he saw spots on the sun. And again, he said the sun is not a perfect sphere. It has something on it. So he said the sun is not perfect sphere. Well, the sun is the brightest object that we can see in the sky. The moon also, the second brightest object, and it's not a perfect sphere. So he starts saying, well, there are things that go against the model of the Greeks. And he said Jupiter is not alone. It has objects that go around Jupiter as well. That means Jupiter could be the center for other things. And then when he looked at Venus, and I remember I told you that Venus has a thick atmosphere made of sulfuric acid and reflects the sunlight so brilliantly, and so on, and that's why it looks very bright in the, sometimes in the evening sky, sometimes in the morning sky, depending on the season. And when he looked at Venus, he starts seeing faces similar to what the moon does. So Venus does that. So if we look at the Ptolemy model, where you can assume that the Earth is the center, and maybe if we argue that Venus is reflecting some light, so we always should see the same thing from Venus. But if Venus is making different phases, the only way that can be explained is by basically assuming that Venus orbits the sun, not the Earth. And that's when Galileo Galilei basically started presenting his observation and saying that the sun should be the center, not the Earth. And many regard Galileo Galilei as the defender. So that's basically enforcing or giving credit to the model of Copernicus, where the sun should be the center, not the Earth. And that goes against the teaching of the church, and that's why he faced the Inquisition. And he wrote a book which called The Dialogue, and in this book it's an argument between two, where trying to convince one that the sun is the center, not the Earth. It's a clever way of doing these things, and of course I think some actually they alerted the Pope to this, and maybe they start telling them that you're the person who looks like them or something like that. Okay. And this is when his problems basically started. And he's a scientist. He's seeing things. He's making observation, and no one can argue with this anymore because the telescope is used by many now to magnify things. And he's not making any magic. He's using a tool and seeing this observation, and people can do that. So this is when it starts causing him problems. And I think this is the clash when it started between religion and science in Europe during that era. So Galileo basically did that. Now, the models collected later, and we'll talk about this puzzle in planetary motion, and we'll introduce here Tycho Brahe. He's mentioned here because he made careful observation. But remember, he was born in 46. And if you recall, when we talked about Copernicus, we said Copernicus died in 1543. So he was born 3 years after the death of Copernicus. And he died in 1601. And if you recall of the observation of Galileo Galilei, that was in 1610. So these observations were made after his death. He is always mentioned or because of his careful observation. I think his personal life, I think his uncle took him, and he had good schooling, and I think he had good funding. So he made an observatory, and he made tools, and he started making careful observation of the stars and the planets. It became precise with his tools that they have. He also may actually look at a supernova that showed no parallax, so something to his credit. And from his observation as well, he kind of entertained the idea that no, the Earth being the Earth is, or the way the Greek model is, maybe that's not a correct one. So he made a model of his own where he said everything orbited the sun, but the sun and the moon orbited the Earth. So you can say that he's aware of the ideas of Copernicus because the model is there. And he's, of course, aware of the model of the Greeks. But somehow, from his careful observation and trying to explain what they see in the night sky, that to him probably was not, did not make sense. And he came with this model. So the moon is orbiting the Earth. So if he only said that the sun is orbit the Earth, so he'll have the same model more or less like Copernicus. But somehow he came up with this model. But he was basically credited with his careful and precise record of what he saw of the Earth, of the planets and the stars. Johann Kepler, who was born in 1571, he died in 1630. Now, two things were available to him. The Copernicus model, where it says that the sun should be the center, not the earth, and the careful observation of Tycho Brahe. And Tycho Brahe was very careful with his record, and he did not allow people to have access to it that easily. And I think in history they say Johannes Kepler was tricking him to get hold of this data and so on. We're not going to go through that. But when Johannes Kepler get hold of the data, and he's good at math and modeling and things like that, he start basically adopting the idea that the sun is the center. But he said Copernicus is wrong in saying that circular motion and uniform circular motion, that means you have circles and so on, because now he had hold of good records, observation, and he started modeling this, and that's when he corrected Copernicus model of how the planets are orbiting the sun. So now I will try to take you through some simple arguments to know the difference between a circle and an ellipse. So I'm not very good with my hands, but if you take a circle, you have a center in the circle, but an ellipse, you can take a circle and you push from the side and it will become something like that. And that's known as an ellipse. And an ellipse, you don't have a center. What you have a focus. So there is one focus here and one focus there. And if you want to draw a circle, you can take a pencil, for example, and you tie a rope to it, and then you fix it here and you go around, and that will give you a circle. If you want to do that, to draw an ellipse, you can take a string and you tie it in this way, but you will decide where the foci will be. So that's one focus and that's the second one, and you stretch and you go around and you'll basically going to get an ellipse this way. So when you try to analyze this, if you go midway along the ellipse, you can cut it in half. This is what we call the major axis here. If you come to the midpoint here, and we can measure it as A, and then we measure how far is the focus from this midpoint here. And we define something that we call eccentricity and give it a symbol E, which is equal to C over A. That means how much you are deviating from a circle. So if this is a circle, if you draw a line this way, everything is at the center here. So C will equal to 0. And A will equal the radius. So in that sense, the eccentricity here will be 0. And you get complete centricity, which is a circle. But eccentricity will be that. So when you analyze a circular object, you try to look at this eccentricity to see if it's really a circle or it's deviating from a circle. And you can see here in this sketches, that's eccentricity of 0.02, that's 0.1, 0.2, 0.4, 0.6. So you can see when it's very small, you can be fooled that what you're looking at is a circle and not an ellipse. So with this, he starts basically realizing that the orbits are not circular, they are elliptical. So for example, if we look at the orbit of the Earth around the sun, it's not it has eccentricity of about 0.0167, which is very small. So you cannot blame those who made observations and they say it's circular or nearly circular because they did not have careful measurement. And that's the role of Brahe, where he made this careful measurement that allowed Johannes Kepler to notice this. So remember what I told you, that the average distance between the Earth and the Sun is 150 million kilometers. We say the average because it may vary, but the difference is very small. It's about 1% or 2%, something like that. It's not that big. Now, when we look at the orbits of the planets around the Sun, we can see that Pluto, and Pluto is regarded as a dwarf planet, or it depends on who you talk to. It has the most extreme eccentricity of 0.248, which close inspection, you may actually tell that it may be nearly circular. So that's how science works. You actually do not rely on one. So scientists, one after the other, they start discovering things and making changes and so on. So the second law of Kepler said the first law is basically the planets orbit the sun in elliptical orbits. And his second law, he said, if you have elliptical orbit, then you cannot go around with uniform circular motion. That means you cannot go around with the same speed or same velocity. So he argued that if you look at what we have here, going from A to B, and then on the other side, you're going from A prime to B prime, and we're exaggerating here to show you a good ellipse. So if the sun is only around in one focus, he said basically the object will sweep equal areas in equal time intervals. So when you're further, this area here will equal to this area here. And they're done in the same time interval. However, if you look at the arc here, AB, and you look at A prime, B prime, well, A prime, B prime is longer than BA. And if they're done in the same time interval, then if you divide this arc by the time, which will give you the speed, in here, it will be bigger than here. And that's why he said, well, the uniform circular motion of Copernicus is wrong, because the orbits of the planets around the Earth are elliptical orbits. And then he found a relation between the period of the planet around the sun and how far it is. And in here it says what he wrote as P, which is the period, and Y here means years squared, equal to A, where this is the average distance between the Earth, between the planet and the sun, in terms of AU, raised to the power 3. So in our case, when we look at the Earth, the period is 1 year, and the average distance is 1 AU. So if you take 1 squared, it's actually equal 1 cubed. This will give you 1 times 1, and this will give you 1 times 1 times 1, which will give you 1 equals to 1. But in other planets, if you know their periods, then you can figure out how, or the average distance of how far they are. And that, the relation here in the x-axis, he's plotting the how far in AU, and in the y-axis here, he's plotting the period, and he got a curve like this, and this curve basically can be explained by this relation here. P in years squared is equal to A cubed squared. So with this, Kepler corrected the model of Copernicus. So you can see how things progress here. And of course, if you look at Kepler, if you look at Copernicus, they were modeling things. Brahe had careful measurements because he had good funding. But when you look at Galileo Galilei, he presented evidence to assert this. And that's why evidence are critical in science. Now, there are many names and golden names that contributed to astronomy, but usually those who made the difference. And that's why they are mentioned here. And I will end up with this statement. I don't know who said this. I was listening to someone. I think he was a Nobel Prize laureate. And he said the Nobel Prize are not given for very intelligent scientists, but it's given to those who discover things that make difference. So I'm just probably there are many names in the course of astronomy, but usually we make at those, they are smart, okay, we're not, but they made a difference. Any questions on these? Any questions? Any questions so far?